Hello, welcome to the video lecture series on digital image processing. Now, in today's lecture, we will discuss about the final phase of image processing, that is image understanding, and which we have termed as object recognition. So, till our last class, we have seen the different representation and description techniques, and we had said that for understanding the images or to recognize the objects present in the images, we have to have a proper representation mechanism, so that the objects or the shapes present in the image can be represented properly. And then for such a representation scheme, we have to have a proper description. From the represented shapes, we have to generate a proper description, so that using these descriptions, the shapes can be matched against a set of similar such descriptions which are kept in the knowledge base. And after this matching, we can identify that the object that we are getting from the image, which particular object it is, or we can roughly classify that which class to which class of the objects which are there in the knowledge base of the computer this current object belongs. So, till our last class, we have seen a number of such representation and description techniques. So, firstly we had obtained some boundary based descriptors, and we have seen that the different boundary based descriptors are shape numbers. The shape number is something which is generated from differential chain code representation of the boundary. We have seen the auto regression coefficients, where for getting this auto regression coefficients, we had to get a polygonal approximation, a polygonal representation of the boundary. Then the corners at vertices in this polygon, they are represented by an auto regression model, and by solving a number of linear equations, we can we can solve for those auto regression coefficients. And these auto regression coefficients or set of auto regression coefficients, that also act as a descriptor of the shape. Then we have seen a boundary signature, and we have said that this boundary signature is nothing but some one dimensional representation of a two dimensional boundary. So, there what we have to do is we have to get the centroid of the shape, and from the centroid of the shape we have to get the distance of different boundary points. And when you get the distance of different boundary points, then from the center the boundary points have to be traced either in the clockwise direction or in the anti-clockwise direction. And the direction of this particular distance, if I plot that distance versus the direction from the centroid of that particular object, then what we get is one dimensional or 1D functional representation of the two dimensional boundary, and that is what we have called as boundary signature. And we have seen that if I have shapes of different types, for different types of shapes we get different types of boundary signatures, and these signatures are obviously they have to be normalized properly, so that the values lies between 0 and 1. And these boundary signatures can also be used for recognition of the shape or shape description purpose. Then the other boundary based descriptor that we have obtained is Fourier descriptor. So, in that case what we have done is we have represented different boundary points, the points lying on the boundary, as a complex number, and if you trace the boundary either in the clockwise direction or in the anti-clockwise direction, then basically what we get is a sequence of complex numbers. And if I take the discrete Fourier transformation of this sequence of complex numbers, then what I get is a set of Fourier coefficients, and in this case in general the set of Fourier coefficients are complex in nature. So, this set of Fourier coefficients they also act as descriptors which can be used for matching purpose or for recognition purpose. Then we have defined we have obtained some more boundary based descriptors like boundary straightness, bending energy, and so on. Then we have also talked about some region based shape descriptors. So, in region based shape descriptors we have seen different descriptors like eccentricity. For eccentricity we have said that it is nothing but the ratio of the length of the major axis and the length of the minor axis of that particular shape. So, what you have to get is we have to obtain the length of the major axis and we have to obtain the length of the minor axis, and the ratio of these two is what is known as eccentricity. Then we have seen another region based shape descriptor which we have said is elongatedness, and for getting this elongatedness what you have to obtain is a minimum bounding rectangle, and the ratio of the sides of this minimum bounding rectangle is defined as this elongatedness. We have also talked about rectangularity, we have also talked about compactness, then we have seen some other moment based descriptors, and we have seen that there are 4 different moment invariants which can be used as descriptors of the shape. Then the other kind of descriptor we have said is, here we want to find out the surface reflectance property of the object present in the image, and we have said that this surface reflectance property, this may be a color or the texture information which are present on the object surface. So, this region based descriptors, say for example, for textures we have talked about the histogram based moments. Similarly, we have talked about the co-occurrence, the descriptors obtained from the co-occurrence matrix of the texture, and we have also seen the different structural, different spectral descriptors of a particular texture. So, all these different types of descriptors or a set of all these different types of descriptors, they can be used for recognition of an object or understanding the object present in the image. Now, you find that out of all this, it is the shape number which is slightly different, because shape number basically gives a chain of different numerical values, say ranging from 0 to 7, and this chain or circle of numerical values actually describe the boundary of the object. Whereas, the other kind of descriptors, we can assume that each of the other descriptors highlight a particular property of the shape. So, if I take a set of such descriptors, if I take n number of such descriptors and put those descriptors in an ordered manner, then what I get is an n dimensional vector. And this n dimensional vector, which is normally called as a feature vector. So, each of these feature vectors represent a particular object or a particular object shape. So, we will see that for different objects or different object shapes, this feature vector is going to be different. So, the recognition can be done based on these feature vectors, because we assume that for different objects they will be different. So, in today's lecture, we will talk about this object recognition problems. So, first we will talk about the recognition technique using the shape number which is obtained from the boundary of the object. Then we will talk about some feature based techniques for object recognition. So, under that we will talk about the linear discriminant function, we will talk about the minimum distance classifier, and we will talk about optimal statistical classifier. So, all these different, the linear discriminant function, the minimum distance classifier or optimal statistical classifier, all these different types of techniques are using the feature vector, as we have said that the feature vector is nothing but an ordered set of the different features or descriptors that we have obtained earlier. And lastly, we will talk about another approach of recognition, which is the neural network based technique, and this neural network based technique also makes use of the feature vectors as the descriptors of different objects or different object shapes. So, the first one that we will talk about today is what we said is the shape number based approach. So, recognition technique using shape number. So, earlier we have talked about the shape number, generation of shape number using 8 directions. So, there we have said that in the 8 direction we have identified the different directions of moves like this. So, this is the direction which was given as 0, this is 1, this was 2, this was 3, this was 4, this was 5, this was 6, and this direction was 7. And using these 8 directions, we had obtained the chain code. We have obtained differential chain code, and then we have obtained the shape number. Now, for simplicity of the discussion, today we will talk about another kind of chain code generation, which does not use 8 directions, but it uses 4 different directions. So, today we will talk about the chain code using 4 directions, and in these 4 directions our direction identifications are like this. So, this direction will be mentioned as 0, this direction is 1, this direction is 2, and this direction is 3. So, if I obtain a differential chain code using these 4 different directions. So, first what we do is we obtain a chain code using the 4 different directions, then you obtain the differential chain code using 4 different directions, and we have seen that this differential chain code, if I consider that to be a cyclic chain, a cyclic set of numbers, then from here from this differential chain code I can redefine a starting point, so that the resulting numerical value will be the minimum, and we have said that that particular numerical value is what we have termed as a shape number. Now, there is another term which is called order of the shape number. Order of shape number. Now, this order of shape number is nothing but the number of digits which are present in the shape number. So, if I have a shape number something like this, say 0, 0, 1, 3, 2, 1, 0, something like this. So, find that in this particular shape number there are 1, 2, 3, 4, 5, 6, 7 different digits. So, the order of this particular shape number will be 7. Now, the problem is, if I want to use the shape number as a descriptor, and this shape number is to be used for recognizing a particular object, or to say that a particular object is similar to one of the set of objects which are present in the knowledge base of the computer, then what you have to do is that this shape number must be independent of the starting point. I mean, whatever starting point we use to generate the shape number, so this generated shape number must be independent of the starting point. And secondly, the order of the shape number of the object shape which we are trying to recognize, and the order of the shape number which is there in our knowledge base, which is stored in the computer, they must be same. Now, the problem is something like this. Suppose I have an object of this form, and I have a similar shape of object, but the size is slightly different. So, this will give me one particular shape number, say S1, this will give me another particular shape number, say S2. So, our first job is, when we want to generate the shape number of this particular object, say O, in that case the shape number that I have to generate must be starting point independent, and at the same time whatever is the order of the shape number of S1, the order of the shape number S2 must be same. So, to obtain this, what you have to do is, we have to align the grid in a particular way, so that our generated shape number is independent of the starting point. And not only that, we have to decide that what should be the grid spacing to generate this particular shape number. So, one way to make it starting point independent is that you align the grids in such a way that the grid is aligned with the principal axis of the particular shape. So, if I have an object say something like this, then our principal axis is this one. So, I want to ensure that the grid that I place, the grid must be aligned with this principal axis, and this is nothing but, as we have said, that major axis, and minor axis is perpendicular to this major axis. So, our grids must be aligned with this major axis and the minor axis. And then to decide about what should be the grid spacing, because this is what will decide about what will be the order of the shape number that we generate. Now, since we are discussing about the chain code using 4 different directions, so you find that if I specify the order of a particular chain code of a rectangle, what you can do is we can enclose this particular shape using a rectangle, okay, and this rectangle has to be divided into a number of cells. So, you can divide this rectangle into a number of cells like this, and this is what will be our grids. So, I have to decide about that how many such cells I should have to generate the shape number of a particular order. So, for doing this, what we do is we consider that what is the eccentricity. We have defined eccentricity earlier. So, we find out what is the eccentricity of this particular shape. And then we generate a rectangle. Suppose we are interested in shape number of order say 18. So, we want to make the order n equal to 18. So, we want to obtain a rectangle of whose shape number will be of order 18, and you find that I have limited number of such possibilities. I can have limited number of shapes or rectangles having shape number of order of the shape number equal to 18, and these possibilities are: I can generate a rectangle of size say 2 by 7, or I can have a rectangle of size say 3 by 6, or I can have a rectangle of size say 4 by 5. So, you find that for all these different rectangles, the shape number, the order of the shape number will be equal to 18. Then suppose the eccentricity of the object shape best matches with the eccentricity of the rectangle 3 by 6. So, what you have to do is we have to put a rectangle of size 3 by 6 centered at the middle point of the major axis of the shape, and these grids must be aligned with the major axis and minor axis of that particular shape. And once I have a rectangle of this particular size 3 by 4 fitted into that particular rectangle of specific eccentricity, then what I can have is, using this form of grid spacing, if I generate the shape number, then that particular shape number will be of order 18. So, depending upon a shape number of which particular order we want, we have to generate rectangles of similar size, and using the corresponding rectangles or the grid spacings, we can generate the shape number. Now, our purpose is recognition. So, what we have got is we have got a shape number S, and this shape number is so obtained that it is starting point independent, and this shape number S is having some order say n, that is the number of digits present in the shape number is equal to n. Now, given two objects, so I have one object O1 and another object O2. For O1 I have the corresponding shape number S1, and for O2 I have the corresponding shape number S2. Now, when I generate this S1, S2, I make sure that they are of same order n. Now, this order n can be varied depending upon spacing of the grids. or on which the shape number is to be calculated. And we have discussed just now that how I can decide about what should be the grid spacing depending upon the shape number of which particular order we want to generate. Okay. Now, then comes a concept of degree of similarity. Now, what is this degree of similarity? When we are given these two particular shape numbers S1 and S2 of a given order, then the degree of similarity, say K, is defined as the maximum order for which the shape numbers S1 and S2 still matches. So, if I generate S1 of say order 4 and S2 say of order 4, then S1 of order 4 and S2 of order 4 will be same. Say S1 of order 6 and S2 of order 6 will be same. S1 of order 8, S2 of order 8 will also be same. But if I find that S1 of order 10 is not same as S2 of order 10, in that case I will say that the degree of similarity between these two shape numbers S1 and S2 or between two object shapes O1 and O2 is equal to 8. So, I define this degree of similarity as, say if I say that SIA is a shape number of object shape A of order I is equal to SIB, this is also the shape number of object shape B of the same order I, then SIA and SIB should be same for all I less than or equal to k, whereas SIA and SIB for all I greater than k, they should not be same. So, in such case, this is the highest order for which the shape number still matches, that is called the degree of similarity of these two shapes A and B. And using this degree of similarity, we can find out whether two given shapes are similar or not. And you find that from here, of course, I can define a distance function, say distance between shapes A and B. This can also be defined as 1 upon the degree of similarity k, because more similar the objects are, the distance between those two object shapes should be less. So, suppose we are given a number of shapes like this in the database, so something like this, and suppose this is a shape which I want to recognize. So, for recognition purpose, what I have to do is, or for matching purpose, what I have to do is, first I have to get all the shape numbers. So, this is object A, this is object B, this is object C, and this is object X which I want to recognize. So, first I have to start with the lowest order, and for 4 connected chain code, the lowest order of the shape number is equal to 4. So, if I find that for the lowest order all these shapes A, B, C and X, they are similar, then I put them as a single node in a tree. So, this is for 4th order. Then I go for 6th order. Then still I may find that A, B, C and X, they are similar. Then at the next order, next higher order, suppose at order 8, I find that B is different, but A, C and X, they are same. Then if I go for 8th order, B will remain to be different, and here I may find that A and C, they are similar, whereas A and X, they are similar, whereas C is different. So, this is our of order 10. And after this, A and X may be different. If I go for say 12th order, I may find that even A and X are becoming different. But at least up to 10th order, of the shape number, I find that A and X are similar and B and C are different. So, at this point I infer that this shape X matches best with shape A, which is there in our knowledge base. So, this is what is called a decision tree, and using this decision tree we can obtain or we can recognize a given shape against a set of shapes which are present in the knowledge base. So, using the shape numbers and using the decision tree and following the concept of the degree of similarity, we can recognize a particular shape using the shape number itself. Now, the next topic that we will discuss is the feature based recognition. And in this case, as I have said, what I assume is every object is represented by a set of features or ordered set of features, which we call as a feature vector. And suppose, say, if a feature vector say f of a particular object contains n number of descriptors or n number of features. Now, each of these features may be either eccentricity, elongatedness and so on. So, I say that this feature vector f is of dimension n. Now, if I consider a n dimensional space, a space of n different dimensions, then this feature vector f will be represented by a point in that n dimensional space. Now, find that if I have a class of similar objects, in that case the feature vectors of every object belonging to that particular class will be similar. So, if I plot all these feature vectors in that n dimensional space, then these different feature vectors, so if I say that the class contains the particular class of objects contains a k number of objects. So, I will get k number of feature vectors, and the points, the k number of points corresponding to these k number of feature vectors in our n dimensional space will be placed close to one another. So, these points will try to form a cluster in the n dimensional space. Now, using this concept that the feature vectors of the objects belonging to a particular class will be very close to each other, and the feature vectors of the objects belonging to different classes will form two different clusters. They are located in two different locations in our n dimensional space. We can design a classifier which can classify an unknown object into one of the known classes. Now, let us see how that can be done. For our discussion purpose and for simplicity, let us assume that dimension of the feature vectors, that is n, is equal to 2. So, if the dimension of the feature vectors is equal to 2, that means every feature vector is represented by a vector of this form. It will have two components, x1 and x2, and every feature vector is nothing but a vector having these two components, x1 and x2. Now, what I do is, let us plot these points in a two dimensional space. Why I am going for two dimension is, it is easier for visualization. So, suppose this horizontal direction is to represent the first component of the feature vector x1, and I take this vertical direction to represent the second component of the feature vector, that is x2. And suppose we have two different classes of objects, and the classes of objects I represented by omega 1 and omega 2. So, omega 1 represents one class of objects and omega 2 represent another class of objects. So, suppose the points belonging to, or the feature vectors of the objects belonging to class omega 1, I represent them by this blue line, blue circles. So, like this, and the feature vectors of all the objects of the objects which belong to class omega 2, I represent them as green circles like this. So, here you find that the feature vectors of the objects belonging to class omega 2, they form a cluster something like this, and the feature vectors of the objects belonging to class omega 1, they form a cluster like this. Now, given such a situation, it is possible that I can design or I can find out a line separating these two regions. Okay. Now, design of the classifier means I have to decide that what should be this line which demarcates between the feature vectors of the objects belonging to class omega 1 and feature vectors of the objects belonging to class omega 2. So, this class on this side represents my class omega 1 and on this side represents my class omega 2. Now, that can be obtained very easily, because from our school day mathematics we know that if we have a straight line, then for the points belonging to one side of the straight line, I will get a value which is greater than 0, and for other sides on the straight line I get a value equal to 1. So, basically what I have to do is I have to get an equation of this straight line, say g x, I call it g x, such that for any point or any vector, say x 1, let me use some other notation because otherwise it will be confusing. So, let me represent them by superscript. So, I say that x superscript 1 is the feature vector of an object belonging to class omega 1, and x superscript 2 is a feature vector for an object belonging to class omega 2. So, I can assume that for all these points x 1, my g x 1 that should be greater than 0, and g x 2 superscript 2 for all the objects belonging to class omega 2, this should be less than 0. So, once I design this g x having this sort of property, then for any unknown feature vector x, if I find that g x is greater than 0, I immediately infer that x belongs to class omega 1, whereas if g x is less than 0, I immediately infer that x belongs to class omega 2. Whereas, of course, g x equal to 0, that is the boundary case, that means these are the feature vectors which fall on this particular line. And such a function g x, this is called a discriminant function. So, I can design a discriminant function which basically divides the entire two dimensional space in two different halves, one half for all objects belonging to class omega 1 and the other half corresponds to the objects belonging to class omega 2, and for any unknown feature vector x, we just find out what is the value of g x. If g x becomes greater than 0, we decide that this particular x belongs to class omega 1. If g x is less than 0, we decide that the particular x belongs to class omega 2. So, the design consideration is we have to find out what is this g x, and this is what we have to do for a two class problem. That means, if we have only two classes of objects. Now, what happens if we have multiple classes of objects? So, suppose we have m number of classes of different objects. So, in such case, the usual practice is for every class you design a discriminant function. That means, I have a set of discriminant functions g 1 x, g 2 x, like this. I have m number of discriminant functions g m x. And in such case, our decision rule will be something like this. The decision rule is, if I find that for a feature vector x, g I x, so g I x is the discriminant function for class omega I. Gix is the discriminant function for class omega I. So, if I find that Gix is greater than Gjx for all j and j is not equal to I, obviously. In that case, I decide that this feature vector or the object having the feature vector x belongs to class omega I. And here you find that the decision boundary between these two classes omega I and omega j is given by Gix minus Gjx, that is equal to 0. Because obviously, for all the feature vectors, all the points lying on the decision boundary, which is the boundary between the class omega I and omega j, I have to have the corresponding functional values to be same. That is, Gix should be same as Gjx. And the usual practice is that you design a discriminator or discriminant function for every pair of classes. That means, we design Gij, which is nothing but Gix minus Gjx. And here you find that for a feature vector x, if I find that Gij will be greater than 0. This clearly says that I must have Gix which is greater than Gjx. So, if I find that Gij is greater than 0, I immediately infer that x belongs to class omega I. Whereas, if Gij is less than 0, I immediately infer that x belongs to class omega j. So, what we have to do in this case is, for every pair of classes, we have to generate a discriminant function of the form Gij. Now, this particular functional form, this gives a basis of designing a number of classifiers. So, one such basic classifier let us discuss, which is called a minimum distance classifier. Minimum distance classifier. So, what is this minimum distance classifier? Suppose I have capital M number of object classes, and for the objects belonging to a particular class, I have a set of feature vectors. So, what I say is, every class, say every ith class is represented by a mean feature vector, where the mean feature vector of object class, say omega I, is obtained as mi equal to 1 upon ni summation of all the feature vectors x for all x belonging to class omega I. So, what it says is, I have say ni number of feature vectors of the objects belonging to class omega I. So, if I take the mean of all those feature vectors, then the mean vector, that is mi, this is a representative of class omega I. So, this I do for each and every class. So, when I have capital M number of classes, I will have capital M number of such representative mean vectors, and these are the representatives of different classes. Then what I do is, given any unknown vector x, what I do is, I find out the Euclidean norm of this vector x from these mean representative classes. So, I just find out dix, which is x minus mi. So, this gives me the Euclidean norm or the Euclidean distance of this feature vector x from the representative of mth class. Okay. So, I will say that this particular feature vector x will belong to that particular class whose distance or Euclidean norm, the distance of whose representative, the mean vector from this particular vector x is the minimum. So, when I have a representatives like this, say this is M1, this may be say M2, this may be say M3, this may be say M4. So, these are the representatives of 4 different classes, and if I have a feature vector x falling somewhere here, then if I compute the Euclidean distance of x from each of these different representatives, I find that the Euclidean distance between x and M3, this is minimum. So, what I say is that this x belongs to class M3. Now, find that what does this Euclidean norm mean? This Euclidean norm is nothing but x minus mi. This Euclidean norm is, if I expand this, it simply becomes x transpose x minus 2x transpose mi plus mi transpose mi. So, what I am saying is this becomes my dix. So, what I am saying is if this dix is minimum for a particular value of I, then x is assigned to that particular class, and that is equivalent to having a discriminant function of the form gix, which is nothing but x transpose mi minus half of mi transpose mi. So, that can be easily obtained, easily argued from this particular expression. So, I will say that this x will belong to that particular class for which this discriminant function gix is the maximum. So, x will be assigned to that particular class for which the gix gives the maximum numerical value. So, this is a particular class of classifier which is known as minimum distance classifier, because we are assigning the vector x to a particular class which gives the minimum distance. Now, following the same approach, we can have a classifier which is called optimum classifier or optimum statistical classifier. So, what is this optimal statistical classifier? Here you find that every feature vector x that is coming from objects belonging to a particular class omega I. Then the job of the classifier is, the classifier does not know that from which class this feature vector x have been generated. So, the classifier, based on its decision rule, has to decide that to which particular class the feature vector x has to be assigned. Okay. Now suppose the classifier decides that x should belong to omega j. So, find that x has been generated from class omega I, but the classifier has decided wrongly that it belongs to class omega j. So, once there is such a wrong decision, then the classifier incurs a loss. So, we represent this loss by say Lij. That means, the loss incurred for taking a decision in favor of class omega j when the actual class is omega I. Then this optimal classifier is designed based on the concept that the average loss of taking a decision will be minimized. So, how we can represent this average loss? So, you find that this average loss can be written as Rx, which is nothing but Lkj into P of omega k given feature vector x. So, what is this Lkj? Lkj is the loss incurred for taking a decision that the feature vector belongs to class omega j, now omega k, and we have to take this summation for k equal to 1 to m, that is for all the possible classes. And what is this p omega k x? P omega k x is the probability of class omega k given a vector x. Now, from our basic probability theory, we know that P A given B can be written as P A probability A into probability of B given A divided by probability of B. Okay. Now, using this, you find now this R j x, the average loss, this can be written as 1 upon probability of x into summation k equal to 1 to capital M, where capital M is the total number of classes, into L k j p x given omega k multiplied by p of omega k. Now, here you find that what is this p x given omega k? P x given omega k is nothing but the probability density functions of the feature vectors belonging to class omega k. And capital P omega k, this is the probability of occurrence of class omega k. Okay. Now, here you find, because this p x will be common to all the functions, to all these loss functions R j x. So, this p x can be removed from this particular expression. So, once I remove this p x, the form of R j x is something like this. R j x can now become L k j into p x given omega k into p omega k, where k is equal to 1 to capital M. So, as we have said that the job of the classifier is to take that particular decision for which the average loss is minimum. So, here the classifier will assign this vector x to a particular class I for which this loss function R I x will be minimum. Okay. Now, usually for a practical purpose, we assume that this loss function L k j, that is the loss incurred for taking a decision in favor of k when the actual class is j, is equal to 0 for taking a correct decision and equal to 1 for taking a wrong decision. So, this L k j, or I can write it as L I j, is actually written as 1 minus delta I j. That means, I am taking a decision that the object belongs to class j, whereas the object actually belongs to class omega I. So, in this particular case, this delta I j, this will be equal to 1 whenever I is equal to j. So, that the loss function becomes equal to 0, and this will be equal to 0 whenever I is not equal to j. So, that the loss functions become equal to 1. And by taking this particular modification, now you find that we can write this loss function R j x, the average loss R j x, which can be written as p x minus p x given omega j into p omega j. So, you find that in this particular case, the feature vector x will be assigned to a class I for which this R I x will be minimum, or we can say that it will be assigned to class I if we find that p x given omega I into p omega I, this is greater than p of x probability density function omega j into the probability of occurrence of class omega j. So, whenever such a situation occurs that p of x given omega I into p omega I is greater than p of x given omega j into p omega j, in that case the feature vector x will be assigned to class omega I. And here you find that this is nothing but, this is equivalent to having a discriminant function of the form g I x, which is equal to p of x given omega I into p of omega I. So, here you find that to obtain such a discriminant function, I need to have two different probability terms. One of the probability terms is the probability distribution of the feature vectors belonging to class omega I, and the second term that I must have is the probability of occurrence of class omega I. So, only after having these two I can have I can design our required discriminant function g I x. So, to obtain these two probability terms, you have to do a lot of experiments. To simplify the matter, what is done is, in most of the cases, you assume a particular probability distribution function or probability density function. And as we have seen that for most of the applications, we normally use Gaussian probability density function. So, if I assume Gaussian probability density function, that is Gaussian PDF, which is of the form p of x given omega I is equal to 1 upon 2 pi to the power n by 2 into c I to the power half exponential minus x minus m I transpose c I inverse into x minus m I, where m I is the mean of the vectors x belonging to class omega I, and c I is the covariance matrix of all the vectors belonging to class omega I. So, from here it can be deduced that a g I x can be obtained, which is of this form. A discriminant function g I x can be written like this: L n p of omega I minus half L n c I minus half x minus m I transpose into c I inverse into x minus m I. So, if we make few further simplifications, that if we say that the covariance matrix for all the classes is same, that is c I equal to c, and all the classes are equally probable, in that case g I x can be further simplified as, it simply becomes minus half into x minus m I transpose c inverse into x minus m I. So, here you find that such a discriminant function again leads to a particular type of minimum distance classifier, and for that minimum distance classifier we have to take this particular function as the distance function, and this is what is known as Mohalanabish distance. So, just by extending the same concept, we can have a probabilistic, this is also called optimal statistical classifier, because it tries to minimize the loss incurred, average loss incurred for taking a particular decision. Now, this type of features can also be used to train a neural network, and we can use a neural network for the recognition purpose. And the type of neural network which is most common for recognition is what is called a multi-layer feed-forward network. So, here it is something like this. In each of these layers, we have a number of neurons. This is called input layer and this is the output layer. The number of neurons in the output layer is same as the number of classes that we have, and the number of neurons in the input layer is same as the dimensionality of the feature vectors. And there are one or more hidden layers. So, these are the hidden layers, and from every layer the neurons are connected to the neurons of the upper layer through some connection weights. So, something like this. So, what you can do is you can train this particular neural network using some feature vectors whose class belongingness are known, so that these weights are adjusted properly, and once the this neural network is trained, then for any given unknown feature vector, the neural network will be able to classify that feature vector into one of the m different classes. So, while training, what you have to do is, suppose we feed a feature vector x which belongs to class say omega I, and we know that if the input is from a class omega I should get an output which is say T I, but actually I get something other than T I. So, in that case what I have an error, and based on the error, the error information is propagated backwards to adjust all these connection weights, and that is why this is also known as back propagation learning. That is, when you train the neural network, what you use is the error back propagation concept for training the neural network. So, we will not go into the details of this neural network approach. So, typically these are the different approaches which can be used for object recognition purpose. Obviously, of course, there are other schemes, like we can represent an object in the form of a graph, and you can go for graph matching techniques for recognition of the objects. So, with this we come to the end of today's lecture. Now, let us see some of the questions based on today's lectures. The first question is, what is order of shape number? How do you define degree of similarity between two shapes? The mean feature vectors of four different object classes are located at 4 vertices of a unit square. Draw the decision boundaries of a minimum distance classifier. Then define Mahalanobis distance. Why the training procedure of a feed-forward multi-layer neural network is termed as back propagation learning, and what is the difference between supervised learning and unsupervised learning. So, with this we come to the end of our video lecture on digital image processing, and I hope that you will find this material quite useful. Thank you.